10 septillion years. That's how long it would take the world's fastest supercomputer to solve a problem that a chip smaller than a coin just solved in under 5 minutes. Say that number out loud and it barely means anything, because the human brain was never built to hold it. So let's try to hold it anyway. 10 septillion is a 10 followed by 24 zeros. The universe itself, from the moment of the Big Bang to this exact second, is only about 13.8 billion years old. That means the calculation this chip performed in the time it takes to make a cup of coffee would have outlasted the universe itself, roughly 1 trillion times over, if you'd handed the job to a classical machine instead. This isn't science fiction. This isn't a movie pitch. This happened in a quiet laboratory in Santa Barbara, California, in December of 2024, when Google's quantum AI team switched on a chip called Willow and asked it to do something almost no one outside a physics department could fully explain, and it answered back faster than the universe has existed. Picture the room for a second. It doesn't look like the control room from a heist film. There are no flashing red lights, no dramatic countdowns. Instead, there's a machine that looks almost absurdly delicate, a tangle of gold-plated wires and mirrored chambers stacked on top of each other, like some kind of futuristic chandelier hanging upside down. That structure is a dilution refrigerator, and its entire job is to take the chip at its core down to a temperature colder than the emptiness of outer space, colder than the far side of the moon at midnight, colder than almost anywhere else in the known universe. Why go to that kind of extreme? Because the chip inside that chamber isn't playing by the same rules as the laptop on your desk or the phone in your pocket. It's playing by the rules of quantum mechanics. And those rules are stranger, more fragile, and far more powerful than anything classical computing has ever touched. To understand why this moment mattered, you have to understand what a normal computer actually is. Every device you've ever used, every phone, every laptop, every server farm humming away in a data center somewhere runs on bits. A bit is a tiny switch that can be in one of 2 states, off or on, 0 or 1. String enough of those switches together, and you get everything. Every photo, every song, every website, every artificial intelligence model on the planet. It's an extraordinary system, but it has a hard boundary. A classical bit can only ever be one thing at a time. A qubit breaks that rule. Thanks to a strange and well-documented quantum property called superposition, a qubit doesn't have to be just 0 or just 1. It can exist in a blend of both possibilities at once, a shifting probabilistic state that only resolves into a definite 0 or 1 the moment you measure it. Now take that single strange qubit and pair it with dozens or hundreds of others, and let them link together through another quantum phenomenon called entanglement, where the state of one particle becomes tied to the state of another, no matter how they're arranged on the chip. Suddenly, you're not just doubling your computing power with every qubit you add. You're growing it exponentially. 2 qubits can represent 4 states simultaneously. 10 qubits can represent over 1,000. 100 qubits can represent more simultaneous states than there are atoms in the observable universe. That is the theoretical promise that has pulled physicists and engineers toward quantum computing for the better part of 4 decades. The problem was never the theory. The problem was building the thing. This idea didn't start in a Silicon Valley boardroom. It started in the early 1980s when physicist Richard Feynman pointed out something that seemed almost like a paradox at the time. He argued that if you wanted to truly simulate nature at its most fundamental level, the behavior of atoms, molecules, and particles, you would need a computer that itself obeyed the laws of quantum mechanics, because classical machines simply buckle under the complexity. A few years later, physicist David Deutsch built on that idea and laid out the theoretical framework for what a quantum computer would actually look like and what it could, in principle, calculate. By the mid-90s, mathematician Peter Shor had shown that a sufficiently powerful quantum computer could, in theory, break the encryption systems that protect nearly all of modern digital security, banking, communications, government secrets, all of it. That single result is part of why governments and corporations have poured billions of dollars into this field ever since. It wasn't just an academic curiosity. It was a technology with the potential to quietly reshape global power, long before anyone had actually built a machine capable of doing it. Because here's the catch that has haunted quantum computing since its earliest days in the 1980s. Qubits are almost unbelievably fragile. A stray vibration, a fluctuation in temperature, a single cosmic ray passing through the lab, even a subatomic particle drifting in from outer space, any of it can be enough to knock a qubit out of its delicate quantum state. Scientists call this decoherence, and for decades, it was the wall that quantum computing kept slamming into. You could build a chip with more qubits, sure, but the more qubits you added, the more errors piled up, and the more errors piled up, the less reliable your answers became. It was like trying to build a taller and taller tower out of sand that kept slipping through your fingers. Every step forward in raw power seemed to come with an equal step backward in accuracy. For years, that trade-off looked less like an engineering problem and more like a law of nature. Physicists tried all sorts of approaches to fight decoherence. Some froze their qubits down to temperatures just a fraction of a degree above absolute zero, hoping the near total absence of heat would keep stray vibrations from creeping in. Others tried isolating their systems inside vacuum chambers, shielding them from magnetic interference, even burying entire labs underground to block out cosmic radiation. All of it helped, a little. None of it solved the underlying problem, because the more qubits you connected together to do useful work, the more opportunities there were for something, anything, to go wrong. It's a bit like trying to have 100 people whisper a secret around a circle without a single word getting garbled along the way. The bigger the circle gets, the harder that becomes. And for a long time, quantum computing looked like it might be permanently capped by its own scale. Google's first real swing at proving quantum computers could outperform classical ones came back in 2019 with an earlier chip called Sycamore. At the time, Google claimed Sycamore had achieved what researchers call quantum supremacy, solving a specific mathematical problem in about 200 seconds that would supposedly take the world's most powerful supercomputer roughly 10,000 years. It was a landmark headline, and it rippled through the tech world fast. But it didn't go unchallenged. IBM, one of Google's biggest rivals in the quantum race, pushed back hard. IBM's researchers argued that with smarter classical algorithms and enough storage, a traditional supercomputer could actually complete the same task in about 2.5 days, not 10,000 years. That's still a massive gap in Google's favor, but it was a world away from the headline number, and it opened the door to a wave of scientific skepticism. Was quantum supremacy real, or was it a moving target that classical computing could always eventually catch up to with clever enough tricks? The disagreement mostly came down to a trade-off between time and memory. IBM's counterargument relied on using an enormous amount of hard drive storage, essentially trading disk space for speed, to simulate the same quantum behavior on a classical machine. It was a clever, legitimate technical argument, and it forced Google's team to sharpen their claims and be more careful about exactly what they meant by supremacy. That back and forth turned out to be healthy for the field as a whole, because it meant that by the time Willow came along 5 years later, both companies and the wider research community had a much clearer, much more rigorous standard for what counted as genuine proof of a quantum advantage. Extraordinary claims were going to need extraordinary, carefully documented evidence, not just a single dramatic headline number. That skepticism is exactly why the Willow announcement in December 2024 mattered so much, and why the people inside Google's quantum AI lab were treating it less like a headline-grabbing stunt and more like the resolution of a 30-year-old scientific argument. Willow is a 105 qubit chip, and on the surface, that number alone doesn't sound especially dramatic. There are chips out there with more qubits than that. What made Willow different wasn't just its size. It was what happened to the error rate as that size increased. Remember the sandcastle problem? The idea that more qubits used to mean more errors? Willow was built to break that pattern entirely. Google's engineers used what's called quantum error correction, an approach where you take a large group of unreliable, error-prone physical qubits and use them together to create a single, far more stable logical qubit. The idea itself wasn't new. Researchers had been chasing it since the 1990s. And what was new, and what had never been convincingly demonstrated before, was watching the error rate actually fall as they scaled the system up, rather than rise. The specific technique Google's engineers used is called a surface code. Picture a grid of physical qubits, laid out like squares on a checkerboard, where most of the squares are dedicated to doing the actual computation, and the rest are dedicated purely to watching for mistakes, constantly checking their neighbors for signs that something has drifted out of place. If an error shows up, the surrounding qubits can detect the pattern and correct it, without ever having to directly measure and therefore destroy the fragile quantum state doing the real work. It's an elegant idea on paper, but for decades it existed mostly as a mathematical proof, something engineers believed should work but had never actually gotten to work in a real physical system at meaningful scale. Every previous attempt hit the same wall. Adding more qubits to catch more errors ended up introducing just as many new errors as it fixed, if not more. Google's team called this crossing below the error threshold, and in their published results they showed that every time they increased the size of their qubit grid, the logical error rate dropped by roughly a factor of 2. That might sound like a small technical detail. It is, in fact, one of the most important results in the history of quantum computing, because it suggests, for the first time with real experimental data, that quantum computers can be scaled up toward genuinely large, genuinely useful sizes without collapsing under the weight of their own errors. Hartmut Neven, who leads Google's quantum AI division, put it in strikingly simple terms when the results were published. He said the team was now past the break-even point, meaning that, for the first time, adding more qubits to correct errors was doing more good than harm. That single sentence represents a threshold that scientists had been chasing, since before some of the engineers on the team were even born. It's the difference between a technology that's theoretically fascinating and a technology that has a real, credible path toward practical use. To prove the point in a way the world could actually see, Google's team ran a benchmark test known as random circuit sampling. Don't worry about the mathematical mechanics of it. What matters is the outcome. It's a task specifically designed to be almost impossible for classical computers to simulate because it involves generating outcomes from an enormously complex quantum system with no shortcuts available. Willow ran that benchmark in under 5 minutes. Google's team then calculated how long it would take one of the fastest supercomputers currently in existence, a machine named Frontier, to complete the exact same task using the best classical algorithms available. Their answer was 10 septillion years, not 10 million, not 10 billion. 10 septillion, a number so large it stops functioning as a quantity in any meaningful sense and starts functioning more like a statement, a way of saying this isn't a difference of degree, it's a difference of kind. It's worth pausing here because this is where the story tends to get exaggerated into something it isn't, and where a wave of sensational headlines and fabricated claims have spread across the internet, some of them inventing shutdowns, mysterious signals, or secret physics. Defying discoveries that never happened. None of that is real. What is real, and what's genuinely strange enough on its own without any embellishment, is a comment that came directly from Google's own team. Neva noted that a calculation of this scale and speed lends support to an idea first proposed decades ago by physicist David Deutsch, the notion that quantum computation might be best explained by the existence of parallel universes, with the computer effectively drawing on parallel branches of reality to perform its calculation. This is known as the many worlds interpretation of quantum mechanics, and it's a serious, long-debated idea within physics, not a fringe theory invented for headlines. But it's important to be precise about what that comment actually was. It was a philosophical observation about how one interpretation of quantum theory might explain the math, not a claim that Google's engineers detected alternate universes, made contact with anything, or witnessed some kind of anomaly. Predictably, that nuance got lost the moment the story hit social media, and it snowballed into exactly the kind of exaggerated mystery box content that now floods search results and video platforms, complete with invented experts, invented shutdowns, and invented dangers that simply never occurred in Google's actual published research. So let's stay grounded in what actually happened and what actually matters, because the real story doesn't need any embellishment to be extraordinary. Willow represents the strongest experimental evidence yet that quantum computers can scale toward practical usefulness without being crushed by their own error rates. That's the headline. Everything else is noise. Now, does that mean Willow is ready to cure diseases, crack every encryption system on Earth, or redesign the periodic table tomorrow? No, and here's where the skepticism that greeted Google's 2019 claims is still worth keeping in mind. The task Willow completed, random circuit sampling, has no practical real-world application on its own. It was chosen specifically because it's a clean, well-defined way to demonstrate a computational gap between quantum and classical systems, not because solving it cures cancer or designs a better battery. Critics, including researchers at IBM and elsewhere, have pointed out that benchmark comparisons like this one depend heavily on which classical algorithms and which classical hardware you choose to compare against, and that the gap tends to shrink every time classical computing scientists get more time to develop cleverer simulation techniques. In other words, don't be surprised if some of these eye-popping comparisons get revised downward over the coming years, the same way the original 2019 quantum supremacy claim did. That doesn't erase the achievement. It just means the real story is a little more careful and a little less cinematic than the viral headlines suggest. There's also a more fundamental limitation worth understanding. 105 qubits, even error-corrected ones, is nowhere near enough to run the kinds of large-scale algorithms that would genuinely transform medicine, materials science, or cryptography. To break modern encryption, using a well-known quantum algorithm called Shor's algorithm, for example, most estimates suggest you'd need a machine with millions of physical qubits working together, not a few hundred. To simulate a genuinely complex new drug molecule or an advanced battery chemistry, researchers likewise expect they'll need machines far larger and far more stable than anything that exists today. Willow isn't that machine. Willow is proof that the fundamental engineering approach needed to eventually build that machine actually works. That's a smaller claim than the headlines suggest, but it's also a far more important one, because it means the path forward isn't purely theoretical anymore. It's a path that's now been demonstrated in a real laboratory with real peer-reviewed published data in the journal Nature, open for the rest of the scientific community to check, challenge, and attempt to replicate. That encryption-breaking scenario, the one made possible by Shor's algorithm, is exactly why cybersecurity researchers and government agencies around the world haven't been waiting around for millions of qubits to show up before taking action. Over the past several years, a coordinated global effort has been underway to develop what's called post-quantum cryptography, new encryption standards specifically designed to remain secure even against a future, fully mature quantum computer. National standards bodies have already begun formally adopting these new algorithms, and major technology companies have started quietly weaving them into browsers, operating systems, and communication platforms. It's a strange kind of preparation, defending against a threat that doesn't fully exist yet, but the logic behind it is straightforward. Sensitive data that gets intercepted and stored today could potentially be decrypted years from now, once a large enough quantum machine finally comes online. Some intelligence agencies are believed to already be collecting encrypted data with exactly that patient long-term strategy in mind, which is part of why progress like Willow's gets watched so closely, not just by physicists, but by governments. Zoom out even further and you start to see why companies, governments, and research institutions around the world are pouring extraordinary resources into this race. Google isn't alone. IBM has its own aggressive quantum roadmap, aiming to build large-scale, fault-tolerant quantum systems within the coming years. Microsoft has pursued a different technical approach, chasing what are called topological qubits, which its researchers believe could be inherently more stable. Companies in China, along with a growing list of well-funded startups, are racing along parallel tracks of their own. This isn't a niche academic pursuit anymore. It's being treated quite openly as one of the defining technological races of this decade, with implications that stretch from medicine and clean energy all the way to national security and global cryptography. Each of these approaches comes with its own trade-offs. Google and IBM have both leaned heavily on what's called superconducting qubit technology, the same basic approach used inside Willow, which requires those extreme and near absolute zero temperatures, but has the advantage of building on manufacturing techniques borrowed from the existing computer chip industry. Other companies and research groups are betting on trapped ion systems, where individual charged atoms are suspended and controlled with lasers, an approach that tends to produce cleaner, more stable qubits, but has historically been slower to operate. Photonic quantum computing, which uses particles of light instead of matter, is another serious contender, prized for being easier to network together over long distances. No single approach has definitively won yet, and it's entirely possible that different quantum technologies end up dominating different kinds of problems, the way graphics, chips, and general processors both found their own separate niches in classical computing. What's changed with Willow is that one of these competing approaches has now cleared a hurdle that many researchers worried might be nearly impossible to clear at all. And that's really the heart of why a story like Willow's captures so much public attention, and also why it gets so easily distorted along the way. The honest version of this story is already dramatic. A team of scientists spent decades chasing a threshold that many in the field worried might not even be physically achievable. The idea that you could make quantum errors shrink instead of grow as you scaled a system up. They chased it through failed prototypes, through skepticism from rivals, through a previous claim that had to be publicly defended and partially walked back. And they chased it through a genuine textbook example of the scientific method working exactly as it's supposed to: publish, get challenged, refine, and try again. And in December of 2024, in a cooled chamber in Santa Barbara, they finally crossed that threshold and proved it with a calculation so fast and so far beyond classical reach that the comparison numbers stopped sounding like science and started sounding like science fiction. That's why the exaggerated versions of this story spread so easily. When the true achievement is already sitting right at the edge of what feels believable, it takes only a small nudge, a fabricated quote, an invented expert, an imagined shutdown, to push it over that edge into something that sounds like a conspiracy thriller instead of a peer-reviewed physics paper. But the real version doesn't need that push. 10 septillion years is already almost impossible to picture. A chip cooled colder than deep space is already almost impossible to picture. An error rate that falls instead of rises as you scale a quantum system up, solving a puzzle physicists had chased since before most of the team working on it was even born, is already almost impossible to picture. None of it needs an invented twist to feel extraordinary because it already is. So where does this actually leave us? Google's own researchers have been fairly candid that Willow is a milestone on a longer road, not a finish line. The next steps involve scaling up the number of logical qubits, extending how long those qubits can maintain their coherence, and eventually building systems large enough to tackle real, practical problems, the kind that could help design new medicines by simulating molecular interactions that are simply too complex for any classical computer to model accurately, or help design next-generation batteries by mapping out chemical reactions at a level of detail no supercomputer on Earth can currently reach, or help optimize massive logistics and financial systems in ways that could ripple through entire economies. None of that is guaranteed to happen quickly. Many researchers in the field expect it could still take a decade or more before quantum computers are reliably solving problems that matter to people outside physics labs. But for the first time, thanks to results like the ones Willow just delivered, that decade-plus timeline feels like an engineering roadmap instead of a hopeful guess. There's a reason this story swept across headlines, spawned a wave of speculative videos, and got twisted into something far stranger than what actually happened in that lab. It's because somewhere underneath all the exaggeration is a genuinely rare kind of moment, the kind where a team of scientists sets out to prove that a decades-old barrier can finally be broken, and then actually breaks it, on camera, in public, in a peer-reviewed journal, for anyone to check their work. 10 septillion years. A number too large to hold in your head, produced by a chip too small to hold in your hand, cooled colder than the emptiest reaches of space, inside a quiet lab in Santa Barbara, in December of 2024. That's not a story that needed embellishing. That's simply what happened. And depending on how the next decade of engineering goes, it might end up being remembered as the moment the entire timeline of computing quietly, irreversibly changed. Think about how many times in history a breakthrough looked small on the day it happened, and only revealed its true size years later once the world caught up to what it meant. The first working transistor in 1947 was a modest lump of germanium wired together on a lab bench, nothing that looked capable of eventually putting a supercomputer in every pocket on Earth. The first working laser in 1960 was dismissed by some engineers as a solution looking for a problem, before it went on to power everything from surgery to the internet's fiber optic backbone. Willow may belong to that same quiet category. A result that reads, on the surface, like a narrow technical milestone about error rates and qubit grids, but that future generations might look back on as the point where quantum computing stopped being a promising theory and started being an inevitability. Nobody in that lab claimed to have unlocked a secret the universe wasn't meant to give up. They didn't need to. They simply did the difficult, patient work of proving a machine built on the strangest rules in physics could finally be trusted to get more reliable, not less, the bigger it grew. That, without a single exaggeration, is one of the most important scientific results of this decade.